Okay. I am the weird last talk because I am not a machine learning guy. I do multi-agent robotics, and I've been starting to push into this idea of remote access robotics. So what I'm going to talk about today is sort of bridging that sim to real gap in a way that is scalable and also that creates the ability for us to have a level playing field where anyone in the world can test on the same hardware, you can compare algorithms, and you don't have to worry about, is there hardware differences? Do we have that system to really do this comparison for? And so the case study for this and everything that I'm going to talk about is based on our work on the Robotarium at Georgia Tech. And so the Robotarium is a remote access multi-robot test bed. The idea is we're trying to democratize access to robotics, and we let anyone around the world absolutely free of charge, as long as you're doing it for academic or educational purposes, use our robots to validate your algorithms in our hardware. So if in the lower, let me make sure I have it right, the lower right here for you guys, this is an overhead video you get returned. So this is an algorithm that is doing covered control to create a logo that I hope you guys can recognize. If you're interested in using it, the website is robotarium.gatech.edu. The only thing we ask for is who you are, where you're from, and what you're using it for. And we also ask for your email address so that the system can autonomously tell you, hey, your experiments are done or not. To give you guys an idea of the actual space, so on the left here is the actual Robotarium. This is in a converted classroom space at Georgia Tech. For an idea of scale, the test bed itself, that ice rink looking thing, is about 14 feet by 12 feet, 4 meters by 3 meters about. We currently have 22 robots. We've been deploying 50 previously. We have a Vicon system for motion tracking, a projector so that you can put down background information, as well as an overhead camera for you to get feedback on. And so the use case here, so really what we're doing is we want anyone to be able to use this. So if you want to use this, users are in the orange side of this development cycle. And what I'm going to pull back the curtain and talk about a little bit more today is the blue side of this development cycle, which is what we do once someone sends me into an experiment. So the first thing is you guys have to come up with your theory. We're not going to do that for you. You have one robot, you have 20 robots, whatever you would like to do, you deploy it, and then you simply need to download our simulator. It's in MATLAB or Python. At the end of the day, you're sending velocity commands to these robots, unicycle velocity commands, linear and angular velocities. We have provided tools. If you don't like that, you like single integrator, we can do that for you. If you like position or pose control, we can do that for you as well. The top left here for you guys is the same algorithm I've shown before in our simulator window, right? So when you're happy with what you see in the simulation, you simply go back to the website, log in, upload your files, give us a little information, how many robots you need, what's the title, what's the experiment, and you send it away. Then we go into actual validation. You would be amazed how many people send us experiments that don't compile, that have a while loop that never ends. So we simply validate to make sure there's nothing crazy is going to happen. And then you're put in a first come, first served queue. It'll get pulled, it'll automatically run, and the robots will come off their charging stations. They come out, they'll do whatever experiment you want to run. And then when it's over, you will get an email. You will get returned automatically a video for you, along with any data you want. You have access to our Vicon system. You'll get all the tracking data, any simulated states that you save, any internal states of the robots that you want. As long as you save it into a MATLAB, a MAT or NumPy file, it'll be uploaded for you to the website. And then ideally, it's probably not going to work because the sim to real gap is a real thing. And so you can iterate and you can figure out what the differences are if your algorithm needs to be improved or if it's just some minor tuning. Great. So to kind of motivate, I encourage this idea of remote access hardware to help bridge the sim to real gap. So to sort of motivate and help the ideas of what the challenges are here, I want to talk briefly about the development cycle that we've gone through and things that we've improved so that we can actually deal with a large number of submissions simultaneously. So we opened to the world in August of 2017. And we ran it similarly to almost any other test bed, experimental test bed you would have seen. Human operators in the room, we have small hardware that's inexpensive, and we make sure that the experiment works. Okay? The original hardware, software, and algorithms is available at this reference. The problem is, unlike local test beds, or similarly if you're deploying a machine learning policy, I don't know what the nominal operation is supposed to look like. So here's a very old video from 2017 of the old robots. These are the same experiment. One works, one doesn't. We'll see if you can figure out which one's which. Okay. So once it starts moving, it's clear which one is supposed to work. But if you don't know what the nominal operation is supposed to be like, this is really difficult to deal with. What's even more frustrating is when an error occurs, it's really challenging to determine where in the pipeline the error has occurred. It could be tracking, it could be communication, it could be hardware failure, it could be just the robot is stuck on a piece of dust on the floor. These are tiny robots. But it could also feasibly be that someone has submitted an algorithm with a mistake, and so they just stop moving, or they're doing formation control and they're not actually moving anything. So on average, when we were deploying actual remote experiments, we would have a failure about every 2 to 3 hours. That's not of running experiments, that's just period during the day. So 4 or 5 times a day, we'd have to come in and figure out what's wrong with the system. And this becomes more of a problem when you look at how many people are actually using this thing. So in the beginning, around August 2017, we were doing less than 50 experiments a month. Now we have over 2,100 users from every continent except for Antarctica. We've run over 9,800 experiments. Each experiment takes about 10 minutes. So you can start doing the math. The small low pink dot in November of 2018 is 42 hours of consecutive experiments, if everything went perfectly, right? So this is just not feasible to do. And so what I'm really going to focus today on is for doing sim to real, for actually deploying things onto hardware and scaling up the numbers of robots. There are a few main top points I want to hit that we've really done improvements on. Hardware, software, tracking, and maintaining hardware safety no matter what. So to start, this is going to be very quick because everyone's using different things. I'm talking about mobile robotic platforms. If you're using an arm, maybe some of this doesn't apply to you. We used to use the GritSpot, which is that little one on the top picture with the yellow hat. This is about 2 centimeters by 2 centimeters to give you an idea of scale. Very, very small, a lot of hand crafting. So depending on who made it, you got wildly different robots. And that's not necessarily good, especially if you want your robots to behave the same way. Its predecessor, the GritSpot X, the larger one, is built entirely standardized. Everything is a standoff or a screw or a plug. There is no hand soldering, there's no hand manipulation. So you wind up with a consistent robot across the way. It's big enough now that you have just off-the-shelf components that are reliable. It's repairable. We've run these robots for 3 years at this point. And so points of failure, motors will die every 6 months. You can pop off 2 screws, plug a new one in, and it's repaired in 30 seconds. The IR sensors burn out, you pop it off, you put a new one in. Capable of autonomous charging. Energy maintenance is the name of the game. As you scale up the number of robots, that's the number of batteries you have to unplug from every robot, plug into a charging system, pull out battery and put in. It's a lot of time. It's much easier if these robots can use, let's say, Qi chargers like on the back, on the bottom picture here. Go sit against, do wireless charging, and also be able to limit their power draw. So if you're designing hardware, make sure you can turn off the really computationally expensive or energy expensive processors. You can turn off the sensors that you're not using. Because if it's charging, you want to make that charge as fast as possible. And enable over-the-air interfacing so that you can actually change the firmware on all of these robots. So to kind of segue into that, software environment is one of the major challenges that we deal with. So if you have the hardware, software becomes extremely challenging. And when we're dealing with remote submissions, one thing we have to worry about is that user scripts can damage or corrupt your software environment. People will delete directories. People will save files in random places. They will overwrite files that you have sitting there just because they submitted it the wrong way. And so you don't want someone's submission or someone that's working in the lab to damage your work down the line because they've changed something you haven't realized about. There's also a lot of system level heterogeneity. This is a very high overview of our architecture, but we have ARM and x86 architectures, different flavors of Linux, Windows, operating systems. And so we need to manage cross-platform dependencies. And we also have application level heterogeneity. And so we want to be able to have a system of software development that is modular and consistent and deals with all of these problems. So the way that we solve this is we heavily utilize Docker. So Docker containers, if you're not familiar with them, they're essentially really lightweight VMs. Lightweight is in quotes because you can make really heavy Docker containers if you wanted to. It's basically a built application, so you can guarantee the correct dependencies for whatever architecture you're sending it out onto. And what we really like, one of the big reasons that we enjoy this is when you submit an experiment, you send it in, we boot up a Docker container for you. If you destroy that environment, that's fine. We'll blow it away. We'll bring up a new Docker container and it will be a fresh new environment for the next person that's being used. The other reason we like Docker is it helps us with maintaining the firmware version across our fleet of robots. So in order to update firmware, you have a few options. If you can't flash over the air, you've got to plug into every robot you have. You have 50 robots, that's 50 times you have to plug in and flash your firmware. You have 100 robots, 1,000 robots, this isn't scalable. If you have over the air, it becomes a little easier because you can SSH, SCP, do whatever you want to do. And if you're a little clever, you can say, well, what if I could just create an automation process to do those? And the issue is when you start getting into hundreds, thousands of robots, you need to make sure all those connections went through, all the firmware was built properly. With Docker, we have the ability to use what's called a Docker registry. And so this is kind of like a Git repository on your own server for your firmware. And so you can be sitting on your server, compile your Docker image for the robots that you have out there, push it to your repository, and then on your robots, just have two containers running. You have one container that's literally looking at, pointed at the server and saying, is there a new firmware being pushed? And as soon as it sees a new firmware, it pulls it down, deploys it. And so you can asynchronously push up a change to your robots. And when they're on, when they're connected, they will automatically sync and be in the same firmware. Tracking is another thing that does not scale well in terms of test beds. Almost every test bed that I have seen in an academic setting has some sort of overhead camera for truth, right? We use Vicon, and it becomes an issue because you need to create N marker configurations where N is going to go from 20 to 50 to 100 to 1,000. And so we need to create 1,000 unique marker configurations. And if you try to do this by hand, they're going to become similar, right? It needs to be unique in every orientation that you have it in. And so what we've come up with is a nice little algorithm where essentially you create NT. So if we're doing 50 robots, we make 500,000 random assignments of points. So in the lower right here, we have our Vicon hat, right? And we're using 5 markers here. So if you haven't used Vicon, blasts out infrared light, reflects off those Perl markers, and it associates it into an object. And this object can't be symmetric and needs to be unique from every other robot, no matter what orientation it's in. And so we put on some constraints, like all these points need to be within a volume, they need to be separated enough from each other. And also for standardization, we don't want to 3D print these. So we quantize how high they are off the hat so that they can be mounted onto screws. And then we have this nice optimization problem at the top where we create a dissimilarity score. And all this is really doing, it's very messy looking, it solves out nicely. But we find the best rotation and translation of every other marker compared to the one that you have and say, how close is that? And what we do is out of the 500,000, take the top 50, the most dissimilar markers, and we generate them. And using this, we've never had to redo them. We've made 200 at one point, and they've all been tracked fine, no issues, no matter what orientation you're in. And the final thing is kind of what has let the Robotarium allow users from all over the world to deploy their experiments without really worrying about the safety of our hardware. And so I'm gonna push this as managing trade-off between user access and hardware safety, because there's always this tug and pull. So if we let users do whatever they want, so this is an experiment on the Robotarium, arguably the worst case scenario, they're going to be told to form a circle, and then they're going to be told all at the same time, drive in a straight line to the other side of this circle, right? What's going to happen? All right, I would like to say no robots were harmed in this video. One ripped off an IR sensor and the other one ripped off an encoder. So 2 robots were harmed in making this video, right? So if we let them do whatever they want, this doesn't last long. We're going to break our robots in the worst case. And in the best case, they're going to be stuck there until someone realizes it, and then they're all going to deep discharge, and maybe we have to replace the batteries. An easy solution, which we have sitting there because we sometimes need it, is we have a Vicon system, right? Oh, this is the same video. So we can track all these robots and we can say, hey, if any 2 robots get too close, we're just going to kill your experiment. Better luck next time. But that's really restrictive, right? This is going to happen sometimes, and a lot of experiments don't care about collision avoidance, right? That's not the point of the submission or the academic or educational application. So What we use we give users access to barrier certificates. And so what this is an optimal controller that is basically minimizing the difference between what the user wants the robots to do and not allowing them to violate safety constraints. So here, these robots are still being told every time they have to drive straight through one another. And what the system is doing is finding what's the closest thing I can do to that, but not allow two robots into any one circle, right? So my safety constraint here is a distance constraint. And so they'll spiral out and they'll get to the other side. This is completely emergent. There's no central person who's figuring out how all these robots should move. This is simply just an optimization and my very old computer that can't render videos, apparently. Great. This will go again, the videos on the next page. To put this into a little more math, for you guys, we have a control affine system, right? And so we have these desired velocities that a user is sending, and we want to minimize the difference. We create an output controller that is the minimum distance between what the user wants to do and what is safe, subject to this this safety constraint, which is a inequality constraint. So in this case, our barrier function, Hij, is a pairwise constraint that says no two robots can get too close. And I don't want to go into the details of the class K function in this, but if you've seen control Lyapunov functions, it's a similar reasoning to how you develop this minimally invasive safety routines. And what's nice about this is that you can add more constraints. So for example, here's one where I just say, robots, we're going to generate random single integrator velocities. And so those arrows indicate the magnitude of the velocities, and it should be constant for all time. The magnitude should be at least. But now, instead of just saying robots can't slam into each other, I'm also saying robots can't leave the boundary either. So we create this barrier, invisible barrier around, and it guarantees safety that you can't run into idle charging robots off the test bed. You can't run into the walls. And this allows people to submit where there's going to be a signal reality gap. There's going to be problems with submissions. And we're able to say that's fine. As long as you put a barrier certificate on top of it, then we won't have any collisions. The other nice thing is, because you were allowed to save anything, if you're worried about training something and you say, well, what if the barriers made it work? You can save your control input before and after the barriers. If it changed, then you know that the barriers took over and made your system safe. Dirty laundry. The organizers asked for some dirty laundry slides, and I love giving dirt about the thing that I've been working on so long. But one of the biggest issues that I see with multi-agent robotics, and especially when you start doing learning at larger scales with multiple agents, hardware heterogeneity is a real problem. So if you have a bunch of robots and you drive them all open loop straight, some of them are going to drive right, some of them are going to drive left, some of them are going to drive straight. And if you do the ensemble, it looks like a lovely distribution. But in reality, if you take the same robot that drives right every time, it has an inherent bias. And so we see a lot of algorithms fail in experiment that succeed in simulation because of this fact. Because depending on this type of robot, the robots that you get out, they're going to behave slightly differently, unless you close the loop on the controllers and do some things like that. Barrier certificates also, while they're great, have some underlying problems. The first is, this is a theorem, and it's a statement about a model. If your model is wrong, then you can't guarantee safety. And so when I mean wrong, I mean if we're flying quads, which we'll show in the next, and the quads fly over one another, that model changes and safety can't be guaranteed anymore. If you constrain too heavily, you're worried way too much about safety. This doesn't say that there's a guaranteed safe control effort that can be applied. And finally, that one of the biggest problems we have is deadlock. If you start safe and your constraint is you guys have to not slam into each other, not moving is a perfectly valid solution, right? That will guarantee the constraint, but is not what the users want to actually happen. So it's something that needs to be worked on a little bit or dealt with. To wrap up just a little bit, the future of remote access hardware. I love the idea of creating test beds that you can have as a level playing field. Anyone can submit to. If you submit a paper to ICRA, you submit the code, you can deploy that directly. You can deploy someone's work so that when you improve on it, you can show whether that's an improvement or which way it's improved. And maybe we can argue about the test bed, that's fine. Where we're going next is to the air. This is showing the barrier certificates in 3D. So this one quad is being flown straight through these other quads that are doing circles. This works. There are many other issues that keep us from flying quads reliably for long durations. However, I invite anyone who is interested in quads to send me an email because we are very close to what I'll call alpha testing. So not open to the entire world, but if you have patience and want to work with us flying quads, I'm more than happy to talk to you about it. Again, if you're interested, the robotarium.govtech.edu is the platform. We have people starting to do machine learning on it. I am more than happy to help along the way. So my contact is up there as well. And I'd like to, of course, I get to come up here and talk about it. But there's a ton of people who have helped work this project and get it to the state where I can come up and tell you how great it is. Thanks.